Jnanam Paramam Dheyam. Knowledge is supreme.
So, in the discussion of benzene so far, we have arrived at a situation where we have learned that out of the 3 possible transitions that are spin allowed, 1 is orbitally allowed as well, 2 are orbitally forbidden. Now, we ask the question, is there any mechanism by which the orbitally forbidden transitions can have some kind of allowedness? And the answer is yes. So, there is always a bypass. There is a main road and there is a bypass. It is just that in our case, the bypass is much narrower than the main road. So, something that is fully allowed will have, if you remember, we had said something, right? What is the kind of extinction coefficient that we can expect for a fully allowed transition? 5000? No, 5 is right, but not 1000. 10 to the power 5. 5000 is 5 into 10 to the power 3. So, 10 to the power 3 to 10 to the power 5, there is a range always, right. Fully allowed transitions typically are associated with epsilon values of 10 to the power 3 to 10 to the power 5. Orbitally forbidden spin allowed transitions are typically associated with a value of 10 to the power 3 to maybe 10 to the power 1, which means that there is some way in which orbitally forbidden spin allowed transitions can take place. To a lesser extent, fine, but it can take place. Spin forbidden transitions have much lower epsilon values, and when we look at benzene, I think this will be manifested very nicely. But the question is, how is it that orbitally forbidden transitions are also associated with non-negligible epsilon values of 10 to the power 1 to 10 to the power 3? And the answer is by Vibronic coupling. So, now we will see quickly what Vibronic coupling is and what effect it has on the spectrum, electronic spectrum of benzene. See, Vibronic coupling means, once again, we are not really going to get into the quantum mechanics of it, because it involves a little higher level discussion of perturbation theory. Let me just write the transition moment integral. Transition moment integral that we have written is something like this. Now, I will write using integrals for a change. Psi s dash, psi s, d tau s. Then we had written integral psi v dash, psi e dash, mu, psi v, psi e, d tau. This d tau is EV, right? It contains electronic and vibronic coordinates. When we worked under Born-Oppenheimer approximation, we said that this can be written as d tau E multiplied by d tau V, right. And then this single integral became a double integral, and we happily separated this integral into a product of an integral in vibrational coordinates and another in electronic coordinates, right. But more often than not, what happens is Born-Oppenheimer approximation may not hold. It is called an approximation, right. It is not a firm rule. Any approximation works within some limit and then it breaks down. And as we have seen earlier in case of our discussion of vibrational spectrum, Born-Oppenheimer approximation does break down, right. So, in this case, if Born-Oppenheimer approximation breaks down, then you cannot really separate this integral anymore. So, what you do is you write this transition moment integral as you expand it as a Taylor series. That is what I am not going to do in detail. You write it as a Taylor series, and then the first term, suppose it is orbitally not allowed, first term will vanish. But in the second term and all, what you will have is, you have to consider this entire thing. So, you might remember that transitions that are not dipole allowed can still be seen by using the quadrupole, right. But when does the quadrupole effect show up? Only when it is dipole forbidden. When the strong effect is not there, then sometimes you see the weak effects. What we are talking about now is also a weak effect. You see it only when the strong effect is not there, that is, a transition is orbitally forbidden, alright. So, when it is orbitally forbidden, now it is not enough to look at the triple product, you have to look at the product of all these 5 functions. This of course conveniently breaks down into x, y, z, alright. In case of benzene at least, right, this psi E is A1G, you do not really have to worry about it, alright. So, what we do have to worry about is this psi V, mu, psi E dashed, psi V dashed, product of these 4 functions. Am I making sense? Have you understood? Right? Now, in fact, we can make it a little easier. What have we considered already? We have considered this already, right? When we are talking about your allowedness, orbital allowedness, we have already considered this direct product, okay, and we have arrived at some symmetry gamma, let us say gamma I, okay, or it can even be sum over I ai gamma I, right. So, if you remember, yeah, so this is what it is, right. We have seen that when we took this direct product, for example, we had A1G plus A2G plus E2G. When we took this direct product A2U and B1U, we had B2G and so on and so forth. So, each of these I can write as sum over ai gamma I, where gamma I is an irreducible representation, right. Of course, it can be possible that only one ai has a non-zero value, everything else is 0, that is fine. Now, what are we worried about now? This is a symmetry sum over I ai gamma I, we have psi V dashed cross sum over I ai gamma I cross psi gamma, what am I doing, psi V, okay. If this triple product contains the totally symmetric representation, then we are done, okay. To keep things simple, let me just write gamma I. Alright. Is there any harm if I write this as gamma V psi V dash cross psi V cross gamma I is the same, right? Does not matter in which I take the product. When will this contain the totally symmetric representation? Yes, when psi V prime cross psi V have the same symmetry as gamma I, right. So, the condition for these to contain, let me stick to A1G for the moment since we are talking about benzene. The condition for these to contain A1G is that this direct product of the symmetries of vibrational wave functions of origin and destination must contain gamma I. Understood? See, so far what were we saying, or rather what are we saying now? We have this kind of idea, this is, anyway, it is fine. And it would have been better if I drew this a little higher up, but it is okay. Suppose I go from here to here, 0 to 1 dash, or suppose I go from here to here, 1 to 0 dash. This 1 to 0 dash, will that take place at room temperature? Usually not, unless it is a very, very low frequency vibration. For normal frequencies that we have, this 1 dash to 0 will be seen only at high temperature, right? It will be a hot band. 0 to 1 dash is possible. Okay. Let us restrict our discussion to 0 to 1 dash and 1 to 0 dash, because in any case 0 to 2 dash and all are always a little less probable than 0 1 dash or 1 dash 0 or 1 0 dash. So, what we are trying to say is this: suppose my origin vibrational level of origin is V equal to 0, and suppose the vibrational level in the destination is V dash equal to 1. Then the direct product of these two vibrational levels must contain the same symmetry as the symmetry that I got using the pure electronic wave functions and the dipole moment. Do you understand? So, if I can have a direct product which has a symmetry of B2G, then B2G cross B2G will give me A1G, right? Then this will become vibronically allowed. If I have a direct product of vibrational levels which is E2G, then E2G cross E2G again will give me a sum which will contain A1G, it will become vibronically allowed. If it has B1G, then this one will become vibronically allowed, E2G, again this singlet A1G to singlet B2U will become vibronically allowed, right. So, we are trying to understand conditions in which an orbitally forbidden transition becomes vibronically allowed, and the conclusion that we have reached is that can happen when the direct product of the vibrational wave functions that are involved has the same symmetry as the direct product of the electronic states involved and a component of the dipole moment. That is too long a sentence, may not be easy to understand, but perhaps this is easy to understand. Will you agree with me if I say that if I have a direct product of vibrational wave functions that is B2G or E2G, then this singlet A1G to singlet B1U should become vibronically allowed, or if I have a direct product that is B1G or E2G, then singlet A1G to singlet B2U will become vibronically allowed, right? Right. I think we will come back to this once again tomorrow, because this part will require maybe half an hour to get absorbed, but it will get absorbed only if you go back and study. But before we close, let me ask you one more thing. We are saying that this psi v and psi v dash are either 0 or 1. What do we already know about the symmetries of V equal to 0 wave function and V equal to 1 wave function? V equal to 0 wave function is totally symmetric. V equal to 1 wave function has the same symmetry as the normal mode, alright. And if I say that in our discussion of vibronic coupling, we restrict ourselves to V equal to 0 and V equal to 1 wave function. See, we are talking, when we talk about vibronic coupling, we are saying that V equal to 0 to V dash equal to 0. This is a pure electronic transition. We want to work with situations where this pure electronic transition is not allowed. So, we are saying that now we talk about 0 to 1 dash or 0 to 1 dash or 1 to 0 dash transitions, vibronic transitions. Okay. Since we restrict ourselves to V equal to 0, V equal to 1 wave function, which means that now we do not even have to worry about the V equal to 0 wave function, because that is A1G, right. So, see, I can simplify this discussion a little further. Since one of them is A1G anyway, all I have to say is psi V equal to 1 should have the same symmetry as gamma I, right, and that has the same symmetry as the normal mode itself. Okay. So, the way to look at it is this: from the orbital part only you generate the direct product. If it contains A1G like it does in the first case, then fine, it is orbitally allowed, we do not have to worry about it anymore. But if it is not orbitally allowed, you do not throw away the direct product. You see what the direct product is, B2G, E2G, B1G, E2G. What we are saying is, in these cases, if I have a normal mode whose symmetry is B1, B2G, then that normal mode can couple with these electronic levels and can make this orbitally forbidden transition vibronically allowed. If I have a normal mode that has E2G symmetry, then the same thing happens. In case of A1G to B2U transition, I need normal modes of B1G or E2G symmetry. Okay? So, that is what we are saying. The first one can be vibronically allowed by B2G and E2G vibrations. The second one is vibronically allowed by B1G and E2G vibrations. Do we have such vibrations? Do we have such vibronic coupling? That is what we will learn tomorrow, and that is what will let us explain the electronic spectrum of benzene.